Diamonds are captivating. Their allure is undeniable, drawing the eye with their sparkling brilliance and unmatched beauty. Their brilliance and fire have mesmerized us for centuries. From ancient civilizations to modern times, diamonds have been cherished and revered. They have adorned the crowns of kings and queens, symbolizing wealth and power. They symbolize love, power, and enduring strength. A diamond engagement ring is a timeless symbol of commitment and eternal love, while in other contexts, diamonds represent unyielding strength and resilience. Deep within Earth, under immense pressure and heat, these gems form. It takes millions of years for carbon atoms to transform into the diamonds we treasure, a process that occurs about 100 miles beneath the Earth's surface. Carbon atoms bond in a tight tetrahedral structure. This unique arrangement is what gives diamonds their remarkable properties, making them the hardest natural substance known to man. This structure gives diamonds their incredible hardness and optical properties. Natural diamonds are rare. Their scarcity adds to their value and allure, making them highly sought after. They are found in specific geological formations. These formations, known as kimberlite pipes, are the primary source of natural diamonds. These formations are often the result of ancient volcanic activity. Volcanic eruptions brought diamonds closer to the Earth's surface, where they can be mined today. Finding these diamonds requires extensive mining. The process is labor-intensive and involves significant effort to extract these precious gems from the Earth. This process can have significant environmental and ethical implications. Mining can lead to habitat destruction, water pollution, and human rights issues, raising concerns about the sustainability and ethics of diamond sourcing. However, what if we could create diamonds ourselves? Advances in technology have made it possible to replicate the natural conditions under which diamonds form. What if we could replicate the conditions of Earth's mantle in a laboratory setting? This process, known as chemical vapor deposition or high-pressure, high-temperature synthesis, allows us to create synthetic diamonds. This is the promise of synthetic diamonds. They offer a sustainable and ethical alternative to natural diamonds, providing the same beauty and durability without the environmental and ethical concerns associated with traditional mining. The dream of creating diamonds in a lab is not new. For centuries, the allure of producing these precious gems artificially has captivated scientists and inventors alike. Early attempts date back to the 19th century, a time when scientific curiosity was burgeoning and the Industrial Revolution was in full swing. Scientists understood the basic composition of diamonds, pure carbon. They knew that diamonds were essentially carbon atoms arranged in a crystal lattice structure, which gave them their remarkable hardness and brilliance. They tried to replicate the extreme conditions under which natural diamonds form. This meant mimicking the high pressures and temperatures found deep within the Earth's mantle, where natural diamonds are created over millions of years. One early method involved dissolving carbon in molten iron. This approach was based on the idea that carbon could be precipitated out of the molten iron to form diamond crystals. The mixture was then subjected to high pressure. Scientists used powerful presses to simulate the intense pressures found deep underground. While these experiments showed promise, the resulting diamonds were small and often flawed. The crystals produced were not of gem quality and had numerous imperfections. The technology of the time simply couldn't fully replicate the extreme conditions needed. Despite their best efforts, the equipment available in the 19th century was not advanced enough to produce high-quality synthetic diamonds. However, these early attempts laid the groundwork for future breakthroughs in diamond synthesis. To create a diamond, one must understand its structure. The journey of a diamond begins deep within the Earth, where extreme pressure and high temperatures transform carbon into this precious gem. Diamonds are made of pure carbon. This carbon undergoes a remarkable transformation, turning from a simple element into one of the hardest substances known to man. But the arrangement of these carbon atoms is what makes them unique. Unlike graphite, where carbon atoms are arranged in layers, diamonds have a more complex structure. Each carbon atom bonds to 4 others in a tetrahedral shape. This tetrahedral bonding creates a rigid, three-dimensional network that is incredibly strong. This incredibly strong three-dimensional network is the key to a diamond's hardness. It is this structure that allows diamonds to withstand immense pressure and resist scratching. The way light interacts with this structure creates a diamond's brilliance. When light enters a diamond, it is bent and refracted in multiple directions. Light enters the diamond and bounces around internally due to its high refractive index. This internal reflection is what gives diamonds their characteristic sparkle. This internal bouncing, or total internal reflection, is what gives diamonds their fire and sparkle. The unique structure of diamonds not only makes them incredibly hard, but also exceptionally beautiful, capturing and reflecting light in a mesmerizing way. By the mid-20th century, scientists made significant breakthroughs. They developed the high-pressure, high-temperature HPHT method. This technique mimics the conditions deep within Earth where natural diamonds form. In the HPHT process, carbon is dissolved in a metallic solvent. This mixture is then placed in a specialized chamber. The chamber generates immense pressure, over 5 GPa, and temperatures exceeding 1500 degrees Celsius. Under these extreme conditions, the carbon atoms bond in the characteristic tetrahedral structure, forming a diamond. An alternative method emerged: chemical vapor deposition, or CVD. This process builds diamonds atom by atom in a controlled environment. It starts with a seed crystal, a small, high-quality diamond. The seed crystal is placed in a chamber filled with carbon-rich gases like methane. The chamber is then heated to around 800 degrees Celsius. At this temperature, the gas molecules break down into individual atoms. The carbon atoms then deposit onto the seed crystal, layer by layer, building a larger diamond. Once created, synthetic diamonds undergo a rigorous process. They are cut, polished, and graded. Skilled artisans use specialized tools to shape the rough diamond into a sparkling gem. The cut determines a diamond's brilliance and fire. Just like natural diamonds, synthetic diamonds are graded based on the 4 C's: carat, clarity, cut, and color. These factors determine a diamond's quality and value. Today, synthetic diamonds are virtually indistinguishable from their natural counterparts. While diamonds are prized for their beauty, their applications go far beyond jewelry. Diamonds are incredibly hard. This makes them ideal for industrial uses such as cutting, drilling, and grinding. Diamonds are also excellent heat conductors. They are used in electronics to dissipate heat and improve performance. Their unique optical properties make them valuable in lasers and other optical devices. Synthetic diamonds are playing an increasingly important role in these fields. The mining of natural diamonds can have devastating consequences. It can lead to deforestation, habitat destruction, and human rights abuses. Synthetic diamonds offer a more ethical and sustainable alternative. Lab-grown diamonds eliminate the need for destructive mining practices. They reduce the demand for conflict diamonds, which fuel violence and instability. Additionally, the controlled environment of a laboratory minimizes the environmental impact of diamond production. The rise of synthetic diamonds has sparked debate about their value. Some argue that only natural diamonds hold true value. They cite their rarity and the natural processes that create them. However, synthetic diamonds are chemically and physically identical to natural diamonds. They exhibit the same brilliance, fire, and durability. The main difference lies in their origin. As technology advances, synthetic diamonds are becoming increasingly affordable, making them an attractive alternative to natural diamonds. The world of diamonds is changing. Synthetic diamonds are no longer a futuristic concept. They are a reality. As technology improves and costs decrease, synthetic diamonds will play an even larger role in various industries. Whether adorning an engagement ring or powering cutting-edge technology, diamonds will continue to fascinate. Synthetic diamonds offer a glimpse into a future where beauty and innovation can go hand in hand with ethical and sustainable practices.